The asteroid didn't kill the dinosaurs. The first 60 minutes did. Everything you think you know about the extinction event that ended the age of reptiles, it's probably wrong. Not completely wrong, but incomplete, simplified, sanitized for textbooks and documentaries that need a beginning, middle, and end that fit neatly into 42 minutes between commercials. The truth is messier and more terrifying. 66 million years ago, a mountain fell from space, 10 kilometers across, moving at 20 kilometers per second, 72,000 kilometers per hour. That's 60 times faster than a bullet, 60 times faster than anything you've ever seen move. It struck what is now the Yucatan Peninsula in Mexico, in a shallow sea over a bed of limestone and gypsum. And in the span of time, it takes you to brew coffee, make breakfast, get ready for work, 60 minutes. The world as it had existed for 165 million years was over. Not dying. Over. Before we go further, if you want to understand how we know what happened in those 60 minutes, how scientists reconstructed this hour of planetary catastrophe with more precision than we can reconstruct what you ate for breakfast last Tuesday, hit subscribe. Because this story isn't just about what happened, it's about how we figured it out, and that might be the most remarkable part of all. Now, let's go back 66 million years, the late Cretaceous. The planet is unrecognizable to modern eyes, but thriving, lush, warm. The continents are still drifting apart. North America and Europe are separated by a much narrower Atlantic. India is an island continent racing north toward Asia. Antarctica is green and forested. And the dinosaurs rule everything. Not just survive. Not just exist. They dominate every terrestrial ecosystem on the planet. Tyrannosaurs in North America. Abelisaurids in South America. Hadrosaurs, duck-billed herbivores the size of buses, roaming in herds that number in the thousands. Ceratopsians with their elaborate frills and horns. Massive sauropods still lumbering through forests in some regions, though they're past their Jurassic peak. The sky belongs to pterosaurs, some with wingspans exceeding 10 meters, the largest flying animals ever to exist. The oceans teem with mosasaurs, ichthyosaurs, plesiosaurs, marine reptiles that make modern sharks look quaint. And beneath it all, in the margins, in the shadows, small furry creatures scurry through underbrush and hide in burrows. Mammals, unremarkable, most no larger than a rat. They've existed alongside dinosaurs for over 150 million years, and in all that time, they've remained marginal. Nocturnal insectivores and omnivores. Survivors, yes, but hardly dominant. It's late morning. The sun is high over what will one day be called the Gulf of Mexico. A Tyrannosaurus rex, one of the apex predators of its age, stands near a riverbank, tearing into the carcass of a hadrosaur. Pterosaurs circle overhead, waiting for scraps. In the distance, a herd of triceratops moves slowly through a forest of flowering plants and conifers. None of them know that in the next 60 seconds, their entire world will begin to end. Far above the atmosphere, beyond the reach of air and weather, something is falling toward them. It's been falling for millions of years, actually, since it was perturbed from the asteroid belt between Mars and Jupiter, perhaps by a collision, perhaps by Jupiter's immense gravity pulling objects into new orbits. For eons, it's traveled through the vacuum of space, a dark rock tumbling silently through the void. But now, after a journey of hundreds of millions of kilometers, it's here, entering Earth's gravity well, accelerating. The planet pulls it faster and faster, and the asteroid, 10 kilometers across, roughly the size of Mount Everest, if you compressed Everest into a dense sphere of rock and metal, begins its final descent. It's moving at 20 kilometers per second. At that speed, it crosses the distance from the Moon to Earth in about 5.5 hours. But once it hits atmosphere, there's no time to react, no time to flee, not even time to look up. The asteroid enters the upper atmosphere somewhere over what is now the Gulf of Mexico. Friction with air molecules, even the thin air of the upper atmosphere, begins to heat its surface. But at these speeds, friction is almost irrelevant. The asteroid is moving so fast that the air in front of it can't get out of the way. It compresses, superheats. The leading edge of the asteroid begins to glow, then becomes a streak of fire visible for thousands of kilometers. If you were standing on the ground, watching the sky, you'd see a second sun appear, bright, brighter than the actual sun. A point of light that grows and grows, descending at an angle, screaming toward the horizon. You'd feel heat on your skin. You'd hear a sound building, a roar that grows louder and deeper, rattling your chest, shaking the ground beneath your feet. But you wouldn't have time to understand what you were seeing, because from the moment the asteroid becomes visible in the sky to the moment it strikes the surface is less than 3 seconds. 3 seconds. The dinosaurs near the impact site don't even have time to look up. The asteroid punches through the atmosphere like it isn't there. At 20 kilometers per second, air might as well be tissue paper. And then, at precisely 0 seconds, we'll call this T+0, it makes contact. The Yucatan Peninsula, 66 million years ago, is a shallow sea. Warm water, maybe 200 meters deep, covering a platform of limestone. Ancient compressed coral and shells, laced with veins of gypsum and anhydrite, minerals rich in sulfur. The asteroid hits the water and the seafloor simultaneously. At these energies, there's no difference between water, rock, and air. Everything is just matter in the way. The leading edge of the asteroid is vaporized instantly, not melted, vaporized, converted directly from solid to gas in a fraction of a millisecond. The water in its path is also vaporized. The limestone sea floor is vaporized, all of it turned into plasma, matter so hot that electrons are stripped from atoms in less time than a neuron can fire. The rest of the asteroid, most of its 10-kilometer mass, continues downward, plowing through vaporized rock and water like a bullet through fog. It's still moving at 20 kilometers per second. The pressure at the impact point exceeds anything found naturally on Earth. We're talking millions of atmospheres, pressures that exist only in the cores of planets. The seafloor doesn't crack, it doesn't shatter, it flows. Solid rock behaves like liquid under these conditions. The asteroid burrows into the Earth's crust, and the crust ripples outward in waves, frozen in time by the sheer speed of the event, but moving nonetheless, like the surface of a pond when you throw a stone, except the pond is made of rock, and the stone is a mountain moving at cosmic velocity. In the first second, T+1, the asteroid has punched through the seafloor and penetrated deep into the crust. The hole it's creating is already 15 kilometers deep and growing. Around the impact point, rock is being simultaneously vaporized, melted, shattered, and ejected upward and outward at velocities that exceed escape velocity. Let me say that again. Rock, solid chunks of the Earth's crust, is being thrown upward so fast that it will leave the planet entirely. Some of this material will arc through the upper atmosphere and land thousands of kilometers away. Some will be thrown so high and so fast that it escapes Earth's gravity and enters orbit around the Sun, becoming a swarm of small asteroids itself. Tiny pieces of Earth flung into space that will orbit for millions of years before perhaps falling back to Earth, or to the Moon, or Mars, long after the dust has settled. The energy released in this first second is beyond human comprehension, but let's try. The impact releases approximately 100 million megatons of energy. To put that in perspective, the most powerful nuclear weapon ever detonated, the Soviet Tsar bomber in 1961, was 50 megatons. This impact is 2 million times more powerful. It's more energy than all of Earth's earthquakes and volcanoes combined over recorded history, released in 1 second. At T+2, the crater is now 20 kilometers deep. The asteroid itself is mostly gone, vaporized, fragmented, mixed with vaporized rock and water into a hellish plasma that's expanding upward and outward in a fireball. The temperature in this fireball exceeds 50,000 degrees Celsius. That's 5 times hotter than the surface of the Sun. The fireball is bright, unimaginably bright. If you were standing 1,000 kilometers away, far enough that you wouldn't die instantly, and you looked toward the horizon, you'd be blinded. Your retinas would burn. The light is that intense. But you wouldn't be standing, because at T+2, something else is happening. The impact has created a shockwave in the Earth's crust. Not through air, through solid rock. Seismic waves radiating outward at several kilometers per second. This is an earthquake, but calling it an earthquake is like calling the sun a light bulb. This is a magnitude 11 earthquake. There is no magnitude 11 on the Richter scale. The scale stops at 10 because nothing in recorded human history has ever exceeded magnitude 9.5. This is beyond the scale. Within 2 seconds, the seismic waves have traveled hundreds of kilometers. The ground is rippling, literally rippling, like water. Forests are swaying, then toppling. Animals are thrown off their feet. And this is just the beginning. At T+3, 3 seconds after impact, the fireball has breached the atmosphere. It's now a dome of superheated plasma, 50 kilometers high and expanding. The dome is so hot that it's emitting thermal radiation in every direction. Anything within 500 kilometers that has a direct line of sight to the fireball is being bathed in infrared and visible light, intense enough to ignite. Trees burst into flame. Not because the fire has reached them, it hasn't, but because the radiant heat is so intense that their surfaces spontaneously combust. Animals are scorched where they stand, their skin and feathers and scales blistering and burning before they can even react. And now, the ejecta begins to fall back. The impact has thrown an estimated 1 trillion tons of material upward. Most of it has gone almost straight up, tens of kilometers, hundreds of kilometers. Some of it has left the atmosphere entirely. But what goes up must come down, and now it's starting to return. This isn't like rain. This is a bombardment. Chunks of rock the size of cars, the size of houses, the size of city blocks, falling from the sky at terminal velocity, or faster, because many were ejected with such force that they're re-entering the atmosphere at hypersonic speeds. Each one is a small meteor. Each one creates its own impact, its own shockwave, its own burst of heat. Within 300 kilometers of the impact site, the sky is literally falling. Boulders rain down by the thousands, cratering the landscape, igniting fires, pulverizing anything they hit. The Tyrannosaurus that was feeding by the river, gone. Vaporized if it was close, incinerated if it was farther, crushed by falling rock if it was farther still. The herd of Triceratops, gone. The pterosaurs, incinerated mid-flight or smashed to the ground by the shockwave. Everything within 300 kilometers of the impact is dead or dying within the first 3 minutes. But this is just the beginning, because now the real destruction starts to spread. At T+5, 5 minutes after impact, the fireball has begun to collapse back on itself, but it's left a scar in the atmosphere. A column of superheated gas and debris rising into the stratosphere like a demonic thunderhead. The energy of the impact has punched a hole in the sky, and through that hole, material continues to fountain upward. The seismic waves have now traveled over 1,000 kilometers. In every direction from the impact site, the ground is shaking violently. Magnitude 11 at the epicenter, but still magnitude 8 or 9 at this distance. Trees are falling, cliffs are collapsing, rivers are sloshing out of their banks. And in the Gulf of Mexico, something catastrophic is happening. The impact occurred in shallow water, and the initial blast vaporized the water and carved a crater deep into the seafloor. But now, water is rushing back in to fill the void. Millions of cubic meters of water, displaced by the explosion, are surging back toward the impact site. But they're not just filling the crater. They're colliding, piling up, forming a dome of water that rises and rises. And then it collapses outward. A mega tsunami. Not the kind of tsunami you see in news footage from modern disasters. Terrible as those are, this is something else entirely. The wave radiating out from the impact site is over 1 kilometer high at its peak. A wall of water taller than the tallest skyscrapers you can imagine, racing outward at hundreds of kilometers per hour. It hits the coastline of what is now Mexico, Texas, Florida, obliterating everything. Forests, river valleys, lowland plains, all swallowed by a moving mountain of water. The wave travels inland for hundreds of kilometers before its energy is finally dissipated. Anything living in its path is drowned, crushed, or swept out to sea when the water recedes. The tsunami crosses the Gulf of Mexico in minutes, hitting coastlines on all sides. It races through the shallow inland seas that cover much of central North America, drowning entire ecosystems. It spreads into the Atlantic and Pacific, diminishing in height as it goes, but still devastating to anything near a coastline. At T+110, 10 minutes after impact, the crater has reached its maximum depth, 40 kilometers. It's punched through the Earth's crust and into the mantle. At the bottom of that crater, rock is so hot and under so much pressure that it's behaving like putty. The walls of the crater are collapsing inward, even as the center begins to rebound. A slow-motion splash frozen in rock, like the droplet in a high-speed photograph of liquid hitting a surface. This rebound will eventually form a central peak in the crater, a mountain rising from the center of the impact site. But for now, the crater is a gaping wound in the planet, 40 kilometers deep and 180 kilometers across. It's the largest impact crater formed on Earth in hundreds of millions of years. And it's just the physical scar. The real damage is spreading far beyond the crater rim. The seismic waves, still radiating outward at several kilometers per second, have now reached the other side of the planet. India, which in the late Cretaceous is an island continent in the southern hemisphere, experiences massive earthquakes. The ground heaves. Mountains shed avalanches. In a geological phenomenon known as antipodal focusing, the seismic energy converges on the point directly opposite the impact site on Earth's surface, and there's evidence, hotly debated but intriguing, that this focusing may have triggered or intensified volcanic activity in what is now the Deccan Traps of India. Everywhere on the planet, the ground is shaking. Not magnitude 11, that's reserved for the impact site, but still magnitude 6, 7, 8, depending on distance. It's the largest seismic event in millions of years. Avalanches cascade down mountain ranges on every continent. Faults slip, triggering secondary earthquakes. Coastal regions experience their own tsunamis as underwater landslides displace seawater. But even as the seismic waves radiate outward through the solid Earth, something faster is spreading through the atmosphere: the shockwave. At T+100s 10, the atmospheric shockwave is racing outward from the impact site at supersonic speeds. It's a wall of compressed air, overpressure measured in atmospheres, not kilopascals. Near the impact, the overpressure was enough to instantly pulverize anything solid. But even at 1,000 kilometers distance, the shockwave is devastating. Imagine standing in an open plain. The sky is dark with ash and smoke. The ground is still shaking from the earthquake. You've survived the heat pulse somehow. Maybe you were in a cave. Maybe you were underwater. Maybe you were just lucky and there was a hill between you and the fireball. And then you hear it, a sound. But calling it a sound doesn't capture it. It's a physical force, a wall of pressure moving through the air. The trees around you bend, then snap. Not from wind. There's no wind yet. They snap from the pressure wave itself, the sudden compression of air hitting them like a solid object. And then the wind comes. Hurricane-force winds following behind the shockwave, gusting at hundreds of kilometers per hour, tearing up everything the pressure wave didn't already destroy. And then the sound hits you. At the impact site, the sound is estimated to have been around 300 decibels. There's no reference for this in human experience. A jet engine at close range is about 140 decibels, loud enough to cause immediate hearing damage. A gunshot is about 160. The Saturn V rocket at launch was about 200. 300 decibels is beyond sound. It's a pressure wave so intense that it would liquefy tissue. Your lungs would rupture. Your internal organs would hemorrhage. You would die from the sound itself before your brain could process that you were hearing anything. But even at 1,000 kilometers, far enough that you're not instantly killed, the sound is still over 200 decibels. Loud enough to cause permanent hearing loss. Loud enough to be physically painful. Loud enough that you feel it in your bones before you hear it. Every animal on the planet hears this sound. Some version of it, attenuated by distance, but audible. A deep, subsonic rumble that shakes the ground and rattles the chest. Animals that were far enough away to survive the initial blast, the heat, the earthquakes, they hear this and they panic. Herds stampede, flocks take flight. Predators and prey flee side by side, driven by a terror deeper than instinct. At T+115, 15 minutes after impact, the initial shockwave has traveled over 3,000 kilometers. That's roughly the distance from New York to Los Angeles. Animals in what is now Montana, Alberta, the Dakotas, they're experiencing hurricane-force winds, deafening sound and earthquake tremors. They don't know what's happening. They can't conceive of what's happening. They just know that the world has gone mad, but the worst is yet to come. Because now, the ejecta, the trillion tons of material thrown into the upper atmosphere and beyond, is beginning its return journey in earnest. Some of it never left the atmosphere. The heavier chunks, the boulders and car-sized rocks, they went up and they came down within minutes, falling back within a few hundred kilometers of the impact site. But the smaller material, pebbles, sand-sized particles, dust, that went higher, much higher. Some of it reached the edge of space. Some of it punched through into the exosphere. And now it's coming back. When an object falls from space, even a small object, it's moving fast, very fast. And when it hits atmosphere, friction converts that kinetic energy into heat. You've seen shooting stars, meteors. Those are typically no bigger than a grain of sand, and they burn up completely from the heat of re-entry, creating a brief streak of light. Now imagine not one meteor. Imagine millions, billions, all re-entering simultaneously, all over the world. At T plus 120, 20 minutes after impact, the sky begins to glow. Survivors, animals that were far enough from the impact to escape the initial blast, the fires, the shockwave, they look up and see something impossible. The sky is filled with streaks of light, thousands of them, tens of thousands, like a meteor shower, but instead of a few shooting stars per hour, it's a continuous barrage. The sky looks like it's on fire, and in a very real sense, it is. Each returning fragment, each tektite, as they're called, droplets of rock that were melted and flung into the sky, is heating the atmosphere as it falls. And there are so many of them, falling over such a wide area, that the cumulative effect is staggering. The atmosphere itself begins to heat up. Not everywhere, not evenly, but in a shell around the planet. At altitudes where the ejecta is re-entering, the air temperature spikes. The thermal radiation from millions of simultaneous re-entries begins to propagate downward. If you're standing on the ground, looking up at this glowing sky, you start to feel heat on your skin. Not the direct blast of thermal radiation from the fireball, that was over in seconds and only affected line-of-sight areas near the impact. This is different. This is diffuse. This is the entire sky becoming a radiant heater. The temperature at ground level begins to rise, slowly at first, then faster. 10 degrees, 20 degrees, 30. Animals that survived the shockwave, that escaped the fires near the impact site, that weathered the earthquakes, they're starting to overheat. Reptiles, which are ectothermic, cold-blooded, begin to suffer almost immediately. Their bodies can't regulate temperature internally. When the environment gets too hot, they get too hot. The hadrosaurs, the ceratopsians, the tyrannosaurs that survived the initial blast, they're panting, seeking shade, seeking water, but there's no escape. The heat is coming from above, from every direction. The sky itself is the enemy. Birds, the small feathered dinosaurs that are the ancestors of modern avians, fare slightly better. They can regulate their body temperature, and many instinctively flee to water, to caves, to any shelter they can find. Some dive into rivers and lakes, submerging themselves to escape the heat. Some of them will survive this way. Not many, but some. Mammals, small and nocturnal, and already adapted to burrowing, retreat underground. They dig deeper into their tunnels, into crevices in rock, into any space that provides insulation from the heat. Their small size is an advantage here. They don't need much space, and they don't need much oxygen. They can wait this out if they can just stay cool enough. At T plus 25 minutes after impact, the thermal pulse reaches its peak. The atmosphere at ground level over large portions of the planet has heated to between 100 and 200 degrees Celsius. That's the boiling point of water. That's hot enough to kill most complex life outright. In regions with direct line of sight to large amounts of re-entering ejecta, particularly the northern hemisphere, where the debris distribution is heaviest, the ground itself is hot. Forests that didn't burn in the initial fires are now igniting from radiant heat alone. No flames have touched them. The air itself is hot enough to cause combustion. Animals caught in the open are dying by the millions, overheating, dehydrating, their lungs seared by superheated air. The large dinosaurs, the ones that dominated the planet for 165 million years, they can't escape this. They're too big to burrow. They're too big to hide. Their mass, which made them dominant predators and successful herbivores, is now their death sentence. Large bodies retain heat. They can't cool down fast enough. A Tyrannosaurus, perhaps one of the last of its kind still alive, stands near a riverbank, gasping for air. Its mouth is open, tongue lolling, trying desperately to cool down through evaporative cooling. But the air is too hot. The water in the river is warm, almost hot. There's no relief. Its vision dims, its legs buckle, and it collapses, joining the thousands of other large dinosaurs dying in the same moment all across the planet. The pterosaurs in the sky are falling. Their wings, so perfectly adapted for flight, are now liabilities. They can't escape the heat by flying higher. The upper atmosphere is where the ejecta is re-entering, where the heat is worst. They can't land. The ground is an oven. They spiral down, wings failing, and crash into forests that are already burning. In the oceans, the surface water is warming rapidly. The thermal pulse doesn't penetrate deep water very effectively, but the top layer, the first 50 meters or so, is heating up. Plankton, the foundation of the marine food web, begin to die. Fish flee to deeper water, but they're followed by predators, the mosasaurs and sharks, that are also desperately seeking cooler temperatures. The shallow seas, the continental shelves where so much marine life thrives, become dead zones. The warm water holds less oxygen. The creatures that can't flee to the deep, the ammonites, the marine reptiles that need to surface to breathe, they're suffocating. At T+30, 30 minutes after impact, the thermal pulse begins to subside. The ejecta is still raining down, but the heaviest re-entry phase is passing. The sky is still glowing, but less intensely. The temperature at ground level begins to drop, but the damage is done. Across the northern hemisphere, forests are burning, not in isolated patches, everywhere. The smoke is already thick enough to block out the sun in some regions. Ash is beginning to fall like snow, coating the ground, the water, the bodies of dead animals. In the oceans, the surface waters are choked with dead plankton, dead fish, the bodies of marine reptiles that couldn't escape the heat. The die-off is catastrophic. The food chain from the bottom up is collapsing. And the survivors, the ones that made it through the heat pulse, they're not safe. Not by a long measure. Because now the fires start to merge. Individual wildfires, ignited by the thermal pulse, by falling ejecta, by lightning strikes from the massive thunderstorms forming in the superheated air. They spread. They meet. They combine into firestorms that generate their own weather patterns, creating fire tornadoes and updrafts strong enough to throw embers kilometers into the air, starting new fires far ahead of the main blaze. At T+35, 35 minutes after impact, something like 30% of Earth's forests are burning. The smoke plume is visible from space, if there were anyone in space to see it. A dark pall spreading across the northern hemisphere, fed by millions of individual fires merging into continental-scale conflagrations. Animals that survive the heat pulse now face a new threat: smoke inhalation. The air is thick with particulates, with carbon monoxide, with all the toxic byproducts of combustion. Breathing becomes difficult. Breathing becomes dangerous. The small mammals in their burrows, they have an advantage here too. Underground, the air is stale but filtered. The smoke doesn't penetrate as deeply. They can survive on less oxygen than larger animals. They wait, breathing shallowly as the world above them burns. The crocodilians, crocodiles and their relatives, have their own advantage. They're semi-aquatic. They can submerge in rivers and swamps, their nostrils just above water, filtering air that's slightly cooler and cleaner than the smoke-choked atmosphere above the surface. They can hold their breath for long periods. They can slow their metabolism and wait. And they do. While the dinosaurs die on the banks, while the pterosaurs fall from the sky, the crocodiles wait in the water. Patient, ancient, survivors of previous mass extinctions, and soon to be survivors of this one too. At T+40, 40 minutes after impact, the seismic waves have circled the planet. They've bounced off the other side and are returning, weaker now but still measurable. The Earth is ringing like a bell, vibrating at frequencies too low for ears to hear, but detectable by any creature pressed against the ground. The tsunamis have crossed oceans. The first wave hit coastlines within minutes, but tsunamis don't come alone. They come in series, wave after wave, each one slightly smaller than the last, pounding coastlines for hours. Low-lying islands are scoured clean. Coastal ecosystems that survived the first wave are destroyed by the second, or the third, or the 10th. The impact crater itself, now 40 kilometers deep and 180 kilometers across, is beginning to settle. The walls are collapsing inward. The central rebound peak is rising, slower than the human eye could perceive, but fast in geological terms. In a few more minutes, the crater will reach its final configuration, a multi-ring basin with a central peak, inner rings, and an outer rim. It will be the largest fresh impact crater on Earth. 66 million years from now, it will be buried under sediment, hidden beneath the jungles and limestone platforms of Mexico. But it will still be there, waiting to be discovered by geologists with ground-penetrating radar and seismic surveys. They'll name it Chicxulub, after a small town near the center of the buried structure. And they'll spend decades studying it, piecing together what happened in these 60 minutes. But right now, at T+140, there's no future. There's only the present, and the present is fire and smoke and death. At T+145, 45 minutes after impact, the winds begin to shift. The firestorms are creating their own weather. Massive updrafts from the heat are pulling air inward from surrounding regions, creating winds that feed the fires. It's a feedback loop. Fire creates heat. Heat creates updrafts. Updrafts pull in fresh oxygen. Oxygen feeds the fire. In some regions, the winds are strong enough to uproot trees that survived the initial shockwave. They're blown over, crashing down, adding more fuel to the inferno. The smoke plume has reached the stratosphere. Unlike normal smoke, which rises and then disperses, this smoke, combined with the dust and ash from the impact, is being injected directly into the upper atmosphere by the sheer energy of the firestorms. It's spreading laterally now, forming a dark blanket that's beginning to encircle the globe. And as it spreads, it blocks sunlight. Not completely, not yet, but enough that in some regions it's already noticeably darker. The sun, which was high in the sky at the time of impact, is now dimmed. It looks like late afternoon, even though only 45 minutes have passed. The temperature, which spiked during the thermal pulse, is now dropping rapidly. The heat from the re-entering ejecta is gone. The fires are still burning, but fire creates localized heat, not global heat. Without sunlight, without the sun's energy reaching the surface, the temperature begins to plummet. In regions far from the fires, the southern hemisphere, remote islands, the polar areas, the temperature drop is already noticeable. It's getting cold, fast. At T+50, 50 minutes after impact, the death toll is staggering. It's impossible to count, impossible even to estimate with precision. But the best models suggest that 75% of all animal species on the planet are already extinct or doomed. Not just individuals, species. All the large dinosaurs are dead or dying. Anything over 25 kilograms that couldn't burrow or couldn't get into water has succumbed to the heat pulse, or the fires, or the smoke. The tyrannosaurs are gone. The hadrosaurs are gone. The ceratopsians are gone. The sauropods, already in decline, are finished. The pterosaurs, gone. Every species, the largest flying animals ever to exist, eliminated in under an hour. In the oceans, the marine reptiles are dying. The mosasaurs, the plesiosaurs, the sea turtles. They need to surface to breathe, and the surface is a hellscape of hot water, toxic smoke, and falling debris. They're suffocating, cooking, or being pelted by ejecta. The ammonites, those elegant shelled cephalopods that have existed for hundreds of millions of years, are dying as the ocean chemistry begins to shift and the food chain collapses. But not everything is dead. Not yet. The small mammals are still alive, huddled in their burrows. The crocodilians are still submerged in rivers and swamps. Some birds, particularly the smaller, more generalist species, are still sheltering in caves, in dense forest understory that hasn't yet caught fire, in any refuge they can find. Some dinosaurs are still alive too. Not the giants, but the small ones. The ones that were already adapting to ecological niches similar to modern birds. They're in trees, in burrows, in rock crevices. They're terrified, burned, injured, but they're alive, for now. At T+155, 55 minutes after impact, the fires are beginning to exhaust their fuel in some regions. Not because they've burned out naturally, but because there's nothing left to burn. Square kilometers of forest reduced to ash and charcoal. The firestorms are still raging in areas with more fuel, but the leading edge of the destruction has passed through some ecosystems entirely. What's left behind is a wasteland. Grey ash covers everything. The ground is still hot, too hot to touch. The air is thick with smoke that reduces visibility to meters. The only sound is the crackling of embers and the distant roar of fires still burning elsewhere. Any animal that emerges from shelter now, driven by thirst, by hunger, by desperation, finds a world transformed. The landmarks are gone. The rivers are choked with ash and debris. The air is toxic. There's no food, no water fit to drink, and it's getting dark. The smoke and ash in the stratosphere have now spread far enough that in some regions, particularly those downwind of the impact site, the sun is almost completely obscured. It's not night, it's something worse. A twilight, a murky, grey half-light that makes it impossible to tell what time of day it is. The temperature continues to drop. Without sunlight, without the greenhouse effect that normally traps heat, the planet is radiating its thermal energy into space and not receiving any in return. In the tropics, it's still warm, 70, 80 degrees. But in temperate zones, it's already down to 50, 40 degrees. And it's still dropping. At T+60, 60 minutes after impact, 1 hour has passed. In that hour, the world has ended. Not the planet. The planet is fine, geologically speaking. It's been hit by asteroids before. It will be hit again. But the ecosystems, the intricate webs of life that have existed for millions of years, they're gone. The large dinosaurs are extinct. Every single species over 25 kilograms, eliminated. Not over millennia, not even over years. In 1 hour, the pterosaurs are extinct. All of them. The skies are empty. The marine reptiles are dying. Most are already dead. The few survivors won't last more than days or weeks. The ammonites, those successful, diverse cephalopods that survived multiple previous mass extinctions, they're finished. They'll be gone within months. 75 to 80% of all species on Earth are extinct, or will be within the next few weeks as the immediate effects of the impact cascade into ecological collapse. But 20 to 25% are still alive, clinging to existence in burrows, in water, in sheltered pockets where fire and heat didn't reach. They don't know they're survivors yet. They don't know that they've made it through the worst 60 minutes in the history of complex life on Earth. They just know they're still breathing. And now, the long dying begins. Because the asteroid didn't kill everything in 1 hour. It killed most things in 1 hour. The rest will die slowly over weeks and months and years as the secondary effects take hold. The smoke and ash in the atmosphere continue to spread. Within days, they'll encircle the globe. The planet will be shrouded in a dark veil that blocks 99% of sunlight. It will stay that way for months, maybe years. Without sunlight, photosynthesis stops. Plants die. Not immediately. Some can survive weeks or even months without light, living off stored energy. But eventually, they die. And when the plants die, the herbivores die. And when the herbivores die, the carnivores die. The food chains collapse, link by link, from the bottom up. The temperature continues to drop. The impact winter sets in. Global average temperatures plunge by 20, 30 degrees Celsius. The tropics become temperate. Temperate zones become subarctic. The polar regions become even more extreme. Animals that survived the fires freeze to death. Plants that survive the heat pulse are killed by frost. Fresh water freezes solid in regions where it hasn't frozen in millions of years. And then, after months or years, after the particulates finally settle out of the atmosphere, after sunlight finally returns, a new threat emerges. The asteroid hit a deposit of limestone and gypsum. Those rocks contained sulfur. When they were vaporized in the impact, that sulfur was injected into the stratosphere as sulfur dioxide. And sulfur dioxide, combined with water vapor, creates sulfuric acid. Acid rain. Not the mild acid rain of industrial pollution. Concentrated acid rain, falling for years, poisoning rivers and lakes, dissolving the shells of marine creatures, killing the seeds and saplings trying to regrow in the ash-covered soil. The oceans acidify. Marine ecosystems, already devastated by the initial impact, collapse further. The calcium carbonate shells of plankton dissolve. The base of the marine food web disintegrates. It will take hundreds of thousands of years for the oceans to recover, millions of years for biodiversity to return to pre-impact levels, 10 million years before ecosystems reach the complexity they had before the asteroid fell. But they will recover, because life is resilient, life is stubborn, life finds a way. The mammals in their burrows, they emerge eventually, days later, weeks later, when the fires have died, when the air is breathable again. They find a world of ash and death. But they also find opportunity. With the large dinosaurs gone, ecological niches are empty. Food sources that were unavailable, too large, too dangerous, too well defended, are now accessible. Dead dinosaurs provide carrion for months. Seeds and roots buried in the ash provide sustenance. The mammals spread. Slowly at first. They're small, they're vulnerable, they're competing with the surviving birds and reptiles. But they adapt, they diversify, they evolve. Within 1 million years, there are mammals the size of dogs. Within 10 million years, there are mammals the size of bears. Within 30 million years, there are mammals in the oceans, mammals in the trees, mammals on every continent. One lineage, surviving in the trees, develops forward-facing eyes for depth perception, grasping hands for manipulating branches, larger brains for social cooperation and problem-solving. Primates. From primates come apes. From apes come hominids. From hominids come humans. We exist because of that hour, because a mountain fell from space and killed the giants that had ruled for 165 million years. Because our ancestors were small enough to hide, generalist enough to adapt, lucky enough to be in the right place when the sky caught fire. We are the descendants of survivors. And that hour, those 60 minutes, 66 million years ago, is written into every cell of our bodies, every synapse in our brains. We are here because they endured. But here's the question that should haunt us. How do we know all this? How did we reconstruct an hour of planetary catastrophe that happened 66 million years before humans even existed? The answer is one of the greatest detective stories in the history of science. And it starts with a thin layer of clay. In 1980, a physicist named Luis Alvarez and his son Walter, a geologist, were studying rock layers in Gubbio, Italy. They were looking at the boundary between the Cretaceous and Paleogene periods, the KPG boundary as it's called. This is the layer of rock that marks the end of the age of dinosaurs. And they noticed something odd. Right at that boundary, there was a thin layer of clay, maybe 1 centimeter thick, that was enriched in iridium. Iridium is a rare element on Earth's surface. It's siderophile. It likes to bond with iron. So most of Earth's iridium sank into the core billions of years ago when the planet was molten. You don't find much iridium in crustal rocks, but you do find it in asteroids. Space rocks have much higher concentrations of iridium because they never differentiated into core and crust. The Alvarezes measured the iridium concentration in that clay layer. It was 30 times higher than the rock layers above and below. 30 times. They published their findings, and they proposed a radical hypothesis. An asteroid impact killed the dinosaurs. The scientific community was skeptical. Mass extinctions were supposed to be gradual, caused by climate change or volcanic activity or sea level fluctuations. The idea that a single catastrophic event could wipe out dominant life forms was too sudden, too violent, too much like science fiction. But then other researchers started looking, and they found the same iridium anomaly at the KPG boundary in Denmark. in Spain, in New Zealand. Everywhere they looked, all around the world, there was this thin layer of iridium-rich clay marking the exact moment the dinosaurs died. That's when the hypothesis became harder to dismiss. An iridium layer distributed globally could only come from one place, space. But if an asteroid hit Earth, where was the crater? Impact craters erode. They fill with sediment. 66 million years is a long time. Plate tectonics could have subducted the crater, pulling it down into the mantle. Or it could be buried under kilometers of rock and soil, invisible from the surface. For over a decade, geologists searched for the smoking gun. And in 1991, they found it. Chicxulub, a small town in the Yucatan Peninsula, Mexico. Geophysicists had done surveys in the region decades earlier, looking for oil. They detected a massive circular structure buried under a kilometer of sediment, 180 kilometers across. At the time, they thought it was a volcanic feature. But when researchers looked at the rocks brought up from drilling operations, they found shocked quartz. Quartz crystals with a distinctive microscopic pattern that only forms under the extreme pressures of an impact. They found tektites, glassy spherules of rock that had been melted and flung into the atmosphere, then cooled rapidly as they fell. They found all the signatures of an impact event, and when they dated the rocks, they got 66 million years, exactly the age of the KPG boundary. The crater had been found. The impact hypothesis was confirmed. But the story didn't end there, because finding the crater was one thing. Understanding what happened in the minutes and hours after impact, that required different kinds of evidence. In the years since Chicxulub was discovered, scientists have used computer simulations to model the impact. They've input the size of the asteroid, 10 kilometers based on the crater dimensions. They've input the velocity, 20 kilometers per second, based on typical asteroid trajectories. They've input the geology of the impact site, limestone and gypsum based on rock samples. And then they've run the simulations, millions of calculations, modeling the physics of hypervelocity impact, the behavior of rock under extreme pressure, the dynamics of ejecta, the propagation of shockwaves. The results match the geological evidence. The models predict a certain distribution of ejecta, and that's exactly what we find in rock layers around the world. They predict shocked quartz and tektites, and that's what we find. They predict global wildfires, and we find charcoal and soot in the KPG boundary layer, distributed worldwide. Every prediction the models make is confirmed by evidence in the rocks. But perhaps the most stunning evidence comes from a site discovered in 2019 in North Dakota, a place called Tanis. Tanis is a fossil site that preserves the first hours after the impact, not millions of years later, not thousands of years later, hours. Here's how we know. The site contains fish that died with tektites, those glassy impact spherules embedded in their gills. The fish inhaled the tektites as they fell from the sky. They were alive when the ejecta was raining down, and then they died, suddenly, buried by a surge of water and sediment that may have been a seiche, a standing wave in an enclosed body of water, triggered by the seismic waves from the impact. The fish are preserved in exquisite detail. You can see the tektites in their gills under a microscope. You can see the panic in their fossilized postures, mouths agape, fins splayed. These are animals that died violently and were buried immediately. Tanis also contains the remains of dinosaurs, turtles, ammonites, plants. all jumbled together in a chaotic deposit that speaks of sudden catastrophic death. It's a snapshot, a frozen moment, the first hours of the end of the Cretaceous. When you look at all this evidence together, the iridium layer, the crater, the computer models, the fossil sites like Tanis, you get a picture of astonishing clarity. We know what happened 66 million years ago with more precision than we know what happened in many historical events from just a few thousand years ago. We know when the asteroid hit, late spring in the northern hemisphere, based on growth patterns in fossil fish bones from Tanis. We know where it hit, Chicxulub, in what is now Mexico. We know how big it was, 10 kilometers across. We know how fast it was moving, 20 kilometers per second. We know what happened in the first seconds: vaporization, crater formation, ejecta launch. We know what happened in the first minutes: fireball, shockwave, thermal pulse. We know what happened in the first hours: re-entering ejecta, global fires, seismic waves circling the planet. We know what happened in the days and weeks after: impact winter, acid rain, ecosystem collapse. And we know who survived and why. Because not everything died. And the survivors, they're the key to understanding not just what happened, but what it means for us. The survivors shared certain traits. They were small. They were generalists, capable of eating a variety of foods, not specialized on one food source that might disappear. They were adaptable, able to tolerate a range of temperatures, conditions, environments. And they were, in many cases, capable of sheltering, burrowing underground, diving underwater, hiding in crevices. The mammals fit all these criteria. Most Cretaceous mammals were small, the size of rats, shrews, possums. They were omnivorous or insectivorous, eating whatever they could find. They were nocturnal, already adapted to operating in darkness, which served them well during the impact winter. And many species burrowed, which protected them from the heat pulse and the fires. They didn't survive because they were superior. They survived because they were suited to the specific catastrophe that occurred. In another world, with a different kind of extinction event, they might have died, and the dinosaurs might have survived. Contingency. That's the word. Contingency matters. The crocodilians survived for similar reasons. They're semi-aquatic, which protected them from the heat pulse and fires. They're ectothermic, which means they have low metabolic requirements. They can go months without eating, surviving on minimal resources during the impact winter. And they're generalists, eating fish, carrion, anything they can catch. The birds that survived were small generalist species, not the large specialized birds, not the flightless ground birds. The small ones, the ones that could eat seeds and insects and whatever else they could find. The ones that could shelter in dense vegetation or rock crevices. In the oceans, the survivors were the fish and sharks that lived in deep water, away from the surface chaos. The creatures that could tolerate low oxygen and survive on falling organic matter. Detritus raining down from the dead ecosystems above. The scavengers and the generalists. Everything else, the specialists, the giants, the creatures exquisitely adapted to the warm, stable Cretaceous world. They died. And here's what that tells us. In a catastrophe, dominance is a liability. Specialization is a liability. Size is a liability. The dinosaurs dominated the planet for 165 million years. They were the most successful large land animals in Earth's history. They filled every ecological niche. They were supremely adapted to their environment, and in 60 minutes, they were gone. Because the environment changed, suddenly, catastrophically, and they couldn't adapt fast enough. The mammals inherited the Earth not because they were better, not because they were smarter or stronger or more advanced. They inherited the Earth because they were lucky enough to be small and adaptable when the sky fell. And over the next 66 million years, they diversified into every niche the dinosaurs once filled. They became the new giants: whales, elephants, rhinoceros. They became the new predators: lions, wolves, bears. They became us. We are the children of catastrophe. We exist because of that hour. But here's the uncomfortable truth. We're not just the children of catastrophe. We're the architects of one. Because right now, at this very moment, we're living through another mass extinction, the 6th mass extinction in Earth's history. And this time, it's not being caused by an asteroid. It's being caused by us. The current extinction rate is estimated to be 100 to 1,000 times higher than the background rate, the normal rate of species loss that occurs without any catastrophic intervention. We're losing species faster than at any time since the asteroid impact. But there's a difference. The asteroid was random, a cosmic accident. There was no intent, no agency. It was just a rock falling through space that happened to intersect Earth's orbit at the wrong moment. Our extinction event is not random. It's a choice, a series of choices. Choices about how we use land, how we harvest resources, how we dispose of waste, how we structure our economies. We're not an asteroid, but our impact on the planet's ecosystems is beginning to rival one. Habitat destruction, climate change, ocean acidification, pollution, over-exploitation of resources. These aren't natural processes. These are human activities. And they're driving species extinct at a rate that, if it continues, could result in a mass extinction event comparable to the KPG boundary. Think about that. We, a species that exists only because our ancestors survived a planetary catastrophe, are now causing a planetary catastrophe. And here's the thing. We know better. The dinosaurs had no warning. They had no concept of asteroids, no ability to see it coming, no capacity to prevent it. When the sky caught fire, they simply died, with no understanding of why. We have warning. We have knowledge. We understand the mechanisms. We can see the trajectory. And we have, at least theoretically, the capacity to change course. The question is, will we? Because the evidence is clear. The science is unambiguous. We are in the early stages of a mass extinction event, and we are the cause. But unlike the asteroid, this is something we can stop. Not easily, not without sacrifice. But it's possible. The asteroid impact teaches us about resilience, about adaptation, about the fact that life persists, even in the face of almost unimaginable catastrophe. But it also teaches us about vulnerability, about how quickly dominant species can fall, about how contingency, luck, chance, being in the right place at the right time, can determine who survives and who doesn't. We are the dominant species on this planet. We have been for thousands of years. We have shaped ecosystems, altered landscapes, driven other species to extinction and domestication and dependency. But dominance is not permanence. The dinosaurs were dominant for 165 million years. We've been around for 300,000. We've been truly dominant, agricultural, technological, global, for maybe 10,000. That's nothing. A blink, a rounding error in geological time. And yet, in that blink, we've changed the planet more profoundly than any species since the bacteria that oxygenated the atmosphere billions of years ago. We've altered the climate. We've redistributed nutrients. We've homogenized ecosystems. We've driven the current extinction crisis. The dinosaurs couldn't prevent their extinction. We can prevent ours, but only if we act, only if we make different choices. And those choices start with understanding what we're facing, not in abstract terms, not as a distant future problem, but as an immediate, urgent crisis that is unfolding right now. The next asteroid, the next 10-kilometer rock that could cause a global catastrophe, we're tracking it. NASA and other space agencies monitor near-Earth objects. We have early warning systems. And we have, as of 2022 with the DART mission, proven technology to deflect an asteroid if we need to. We've solved that problem. The random cosmic accident that ended the age of dinosaurs, we can prevent that now. But the extinction event we're causing? That's harder, because it requires us to change ourselves, our behaviors, our economies, our priorities. It requires us to value long-term survival over short-term profit, to value biodiversity over convenience, to value the future over the present. And that's difficult, because evolution didn't wire us for long-term thinking. We're descendants of primates that needed to worry about finding food today, avoiding predators today, surviving until tomorrow. We're not naturally inclined to think in terms of decades or centuries. But we can learn. We can adapt. That's what made us successful in the first place. Our capacity for learning, for transmitting knowledge across generations, for cooperation on scales larger than immediate family groups. We are, in a very real sense, an intelligent species. The question is whether intelligence is enough. The mammals survived the asteroid because they were small and adaptable. We've survived as a species because we're intelligent and cooperative. But intelligence alone doesn't guarantee survival. It has to be applied. It has to be used to make better choices. And that's where we are now, at a choice point. Not as dramatic as an asteroid impact, not as sudden, but just as consequential. We can choose to continue on our current trajectory, degrading ecosystems, driving species extinct, destabilizing the climate, and hope that somehow we'll adapt, somehow we'll muddle through, somehow technology will save us at the last moment. Or we can choose to change course, to prioritize sustainability, to protect biodiversity, to stabilize the climate before we cross tipping points that make catastrophic change irreversible. One path leads to a diminished world, fewer species, simplified ecosystems, a planet that's still habitable, maybe, but impoverished. A planet where future generations will read about the diversity and richness that once existed and wonder why we didn't do more to preserve it. The other path leads to a world where we coexist with the rest of life on this planet, where we manage our impact, where we recognize that we're not separate from nature. We are nature. We're part of the same web of life that includes everything from bacteria to blue whales. And when we damage that web, we damage ourselves. The dinosaurs didn't have a choice. We do. And 66 million years from now, if there are intelligent descendants looking back at this moment, what will they say about us? Will they say we were the species that had the knowledge and the technology to prevent a mass extinction and didn't? Or will they say we were the species that looked at the trajectory we were on, understood the consequences, and changed course? That's the question before us. And the answer will be written not in words, but in actions, in policies, in priorities, in the choices we make today that will echo forward through geological time. The mammals that survived the asteroid didn't know they were survivors. They were just trying to live through the next hour, the next day, the next week. They didn't have the luxury of understanding the scope of what was happening. We do. We know what's happening. We know what's at stake. We know what the costs of inaction are, and we know what the costs of action are. And the costs of action are far, far lower than the costs of inaction. Changing our energy systems, protecting habitats, reducing emissions. These are expensive, yes. They require investment. They require sacrifice. They require changing systems that have been in place for decades or centuries. But the cost of not doing those things, the cost of continuing on our current path, that's measured in lost species, lost ecosystems, lost stability, and ultimately, potentially, lost civilization. Because make no mistake, we are not separate from the systems we're degrading. We depend on them for food, for water, for climate stability, for the resources that underpin our economies. When those systems collapse, and they will collapse if we push them hard enough, we collapse with them. The dinosaurs learned that lesson. They couldn't adapt fast enough when their world changed in 60 minutes. Our world is changing over decades. We have time. Not much, but some. The question is whether we'll use it. 66 million years ago, a rock fell from space, and in 1 hour, the age of dinosaurs ended. The survivors, small, adaptable, generalist creatures, inherited a devastated world and rebuilt it into something new, something rich, something complex. We are the descendants of those survivors. We carry their resilience in our genes. We carry their adaptability in our capacity for learning and cooperation. But we also carry a responsibility they never had. The responsibility of knowing what we're doing, of understanding the consequences, of having the power to choose a different path. The clock that started ticking 66 million years ago never stopped. Life goes on. Evolution continues. Ecosystems recover given time. But individual species, dominant species, successful species, species that thought they would last forever, they can vanish in an hour, or in a century, or in a moment of cosmic bad luck. The dinosaurs couldn't save themselves. We can. The question is, will we? The asteroid was an accident. What we do next is a choice. And that choice will determine not just our future, but the future of every species we share this planet with. Every forest, every ocean, every river, every mountain, all of it is shaped by what we do now. 66 million years ago, an hour changed everything. What will we do with ours?